in 10.2 we will. Anyone I haven't heard from today would like to look at
I
this?
can read it.
Okay, thank you.
A teacher gives an exam with 20 multiple choice questions, each with 4 possible answers. The teacher's null hypothesis is that a certain student is just guessing, and the population proportion of success is 0.25. Suppose the teacher conducts a test with a significance level of 0.01. Write a sentence describing the significance level in the context of the hypothesis.
Okay, so first let's look at a little picture here. Like I always, it's very easy to explain, and I'm hoping that this will trigger your memory and you will understand this better. So the null hypothesis is p equals 0.25. Alpha is 0.01. And they're asking us to write the level of significance in the context of the hypothesis test. Okay, so he says it is a teacher's null hypothesis that a certain student is just guessing, and the population proportion of success is 0.25. Okay, so this is the null hypothesis. I don't know, she didn't say increasing, decreasing, so the only option I see here is this, right? And they're only trying us to, or they're asking us to identify what this means. So it means that rejecting a null hypothesis that is true will give us this error. So I will read the options that they give us, but this is the probability of, so this is type 1, which is reject the null hypothesis, this, say it's different but not equal to, reject H naught, when in fact H naught is true. That's the type 1 error. So now let's read and see what they want. The probability of saying the student is not guessing when the statement is actually guessing is 0.01. The student is guessing is 0.01. Of saying the student is not guessing when the student is not guessing. Of saying the student is guessing when the student is guessing is this. Okay. Okay, so we have to analyze and think a little bit about this. So we are rejecting the null hypothesis when in fact the null hypothesis is true. So the probability of saying that the student is not guessing when the student is actually guessing is 0.01. So we reject the null hypothesis, we reject the p equals 0.25 when in fact it is true. No, that's not the probability the student is guessing. No, the probability of saying the student is not guessing when the student is not guessing. No. Probability of saying that the student is guessing when the student is guessing. No. That the student is not guessing. The probability of saying that the student is guessing when the student is actually not guessing. So we reject the null hypothesis when in fact he's actually guessing. So they're trying to confuse us as much as possible. Okay, so all these are just sand in our eyes. So it's the probability of saying that the student is not guessing. So reject the null hypothesis, and I make the error because he's actually guessing, right? So that is the type 1 error in this case, which is alpha. Remember, alpha is always the type 1 error, or alpha or significance level. Okay, so now let's see how we put this in practice for proportions directly. Any questions? Have you tried anything from 10.1? Do you need us to go back to any of those problems from 10.1? Anyone? Okay, so let's pick and choose from here. We'll do as many as we can. And then next week, we'll finish up with the mean and the two sample study. Okay, any preference? Anyone? Is anyone with me?
Can we do question number 7?
Let's start with 7. Very good. Jen performed the study and obtained a p-value of 1.24. Okay, so let's stop for a second. So remember, we talked about alpha and p-value as probabilities. These are probabilities. Okay, so what do we know about any probability? Anyone? Evan, what do we know about probabilities? Alex, are you with us? Okay, Ethan, are you with us?
Yeah, I'm with you.
Okay, what do you know? What do we know about probabilities? From what we learned this semester.
Yeah, I'm actually not sure.
Okay, anyone else? Mani?
I'm not sure either.
Can anyone help us? What do we know about probabilities?
Are we using the null hypothesis in this example?
No, just what we learned already throughout the semester about probabilities.
Oh yeah, I'll be honest. I don't really remember that.
Okay, anyone?
Wouldn't it be probability it's greater than or equal to 0, but less than or equal to 1?
Thank you very much.
Doesn't it have to? Never mind.
So we wrote this, right, several times. So here's what she says. She found a p-value of 1.24.
And it could be she made an error. It's not possible to get a p-value of 1.24.
Absolutely, absolutely. We can never get a probability of 1.24. That's why, if you remember, I said many times, if you get with a calculator 5.39 and you put that as a probability, then it will break my heart. Good. So let's look at this one, by the way. For each graph, state whether the shaded area could represent a p-value. Choose the correct answer below. Can this represent a p-value? What do you think? From all the graphs we looked at, and we graphed it several times today, can this represent a p-value? Of course, of course. So let's see. The shaded area could be a p-value for a test with a two-sided alternative. This is not a two-sided alternative because it includes a shaded tail and an unshaded tail. No. The shaded area could not be. No. The shaded area could be a p-value for a test with a one-sided alternative hypothesis because it includes a single tail area. Of course. The shaded area could not be a p-value because it includes tail areas only. What does that mean? Who knows? Good. Okay, let's see this one. Anyone else? Could this be a p-value?
Yeah.
Good. Which one will you pick from A, B, C, and D?
Would be a C again.
So the shaded area could be a p-value for a test of one-side alternative hypothesis because it includes a single tail area. Absolutely. Well done. Good. What about here? Could it represent a p-value? Yes, it could.
It would be C.
It would be C. The shaded area could be a p-value for a test with a two-tailed alternative hypothesis since both tails are equal size. Excellent.
I have a quick question about.
Please. Yes. Yes.
Well, the one that we're on. My bad.
Oh.
So if the p-value, like area, if one is bigger than the other, then it would not be.
Correct. If it's a two-tailed test, it has to be equally divided into the two areas, like with the alpha. Very good question. So when we have a two-tailed test, alpha has to be divided. So for example, if I have 0.05, then this is half of 0.05 and this is half of 0.05, right? So this will be 0.05 over 2 and this will be 0.05 over 2. The same thing with the p-value. Because we are comparing something here. So it will be a little bit on this tail and a little bit in this tail. I'll show you with the graphing calculator when we get to an example in a minute. I like the calculator, how it does. This is impossible, right? This cannot be a p-value. P-value like alpha has to be in the tails, either one or the other or both. Could not be a p-value because it includes could not be a p-value because it does not include tail areas. Of course, if it's not in the tail areas, it cannot be a p-value. Absolutely. Okay, so finally, let's get to a test. Okay, let's also do this one, and then I'd like to illustrate with different tests situations. The test is the same. It's only one test. So see, we have z to be, they're given to us 0.45, 1.37, negative 1.91, and negative 2.97. So let me stop sharing. Again, the graph tells us everything. So remember the z distribution. We know that it's normal, standard normal, with the mean 0 and the standard deviation 1. Minus 1 plus 1, minus 2 plus 2, minus 3 plus 3. So now I'm going to picture these z's. 0.45. 0.45 is somewhere here. 1.37 is somewhere here. Negative 1.91 is somewhere here. And negative 2.97 is somewhere here. We're asked which of these points will have the smallest p-value. For this one, the p-value will be this. Or maybe in two tails. For this one, the p-value will be this. For this one, the p-value will be this. And for this one, the p-value will be this. Which of these is the smallest p-value? Anyone? Maddie, would you like to try?
Honestly, I'm still a little bit confused.
Okay, that's okay. Gabe?
I'm a little confused as well. I'm sorry.
That's okay, but that's why I'm asking, because I want to make sure that my students understand what I'm doing. So from the orange, black, blue, and green, which one is the smallest area?
The green area?
Of course, which is for this number. This number is the furthest away from 0. It will have the smallest p-value possible from all of them.
So would negative 1.91 be the blue area then?
Exactly. Oh, I'm sorry. So maybe that's what's okay. So negative 1.91, 0.45, 1.37. These are just numbers between negative 3 and 3. Good. So let's go back. So here it is. That's the smallest p-value from all of them. The z-score closest to 0 has the largest. The z-score furthest from 1. The z-score furthest from 0 has the smallest. And the z-score closest to 0. Which one do I pick?
C.
Of course. The further away from 0 it is, from 0, not from 1, right? Because 0 is the mean, not 1. Has the smallest p-value. Awesome. Great job. Okay, the p0, we already said that this is the population proportion according to the null hypothesis. That's why it's labeled with that 0, because it's the same with it's coming from the null hypothesis. Okay, so now I would like us to here's our first example. So let's start. I'll read this one. A certain drug is used to treat asthma. In a clinical trial of the drug, 16 of 291, okay, 16 out of 291 is our p hat, proportion of the sample. X is the number of people with that characteristic, and n is the sample size. So this is what I have from the very first sentence. Let's see